All right, let's get this online learning underway. All right, so we're going to start with lesson 9.1. As promised, before we left for spring break, we're going to learn our third and final type of graph for the school year. So before we get there, let's kind of review where you've been. You don't need to write these on your notes, just to kind of show you. We spent the beginning first semester, or all of first semester, any graph that we dealt with was linear. So something that creates a line. And then when we finished up chapter 7 this semester, we talked about things that are exponential in nature. So here's examples of both those graphs. So let's add in our third type of graph, which we like to call a quadratic function. All right, so a quadratic function is nonlinear. And it can be written in standard form. As, and we've looked at this before, but we're going to use it quite a bit in this chapter. So we're going to say y equals a x squared. So a is our leading coefficient, plus bx. B is always in front of our linear term, and then plus c, which is our constant. Now, if you look at the definition of this, it also adds in the fact that this is true when a is not equal to 0, meaning that first term has to be there. The only value that it can't be for a is a 0. All right, what do we call these graphs? They are called parabolas. When we look at them, they are U-shaped in nature. And again, related to what we like to call a quadratic, things where the largest degree is 2. So today our focus, or in this set of notes, our focus is to look at the most basic version of a quadratic function, which we like to call the parent function. And then we're going to graph a few of these parabolas that are in a really nice location right off of the y-axis. And then we're going to talk about ways in which they compare to the parent. Then in our next lesson, we're going to try to move this graph around and kind of move it off of our y-axis so that we can determine how we find out what its points are based on that. So first, let's look at the pieces of it so we know how to graph these by hand. So first off, we have what we like to call the parent function, meaning the most basic of functions. For a quadratic, that would just be y equals x squared with a leading coefficient of 1. So nothing else, just a basic. It has the quadratic term. That graph looks like this. So if you want to pause and give yourself a second to plot that, you can. All right, this point down here, I'm going to go ahead and put it in a little bit bigger of a dot. This point here, let me go bigger, is the lowest or highest point of our graph. So you'll notice once we graph a few of these, the parabola can either open up or down. But this point, which is located directly in the center of the graph or in the middle, is called our vertex. It has a lot of important parts for us that we'll talk about as we go through these first few lessons. Now, since it is U-shaped, it also means it's symmetric. So this dashed line that I have in blue, its purpose is more just to help you get it graphed. It's not actually part of the graph, but it does divide it in half. So when we go to graph this here in a little bit, you in essence just need to find half the points and the others just reflect over. But it divides it into two symmetric parts. So two sides that are identical. We call this the axis of symmetry. So those kind of the parts of the parabola. Now again, for today, those are going to land in a pretty nice spot. Tomorrow, in the next lesson, we're going to look at how to find the values of those two items when we know it's not situated on the y-axis. All right, so our goal is to get that kind of practice down, but also to determine the ways in which the parent function can move around using different transformations. So first, we're going to play around with this front value, and we're going to specify that it is larger than 1. So in the parent function, it is 1. In this particular equation, we're going to change it to a 3 and see what that does to our graph. Now, when you go to graph parabolas of any type, we're going to make an XY table to determine the values or the points that we need to plot. When you make this table, our goal is to place our vertex in the center. For this set of notes, that vertex is always going to be with an x coordinate of 0. Oops. When you determine the rest of your domain, you're going to build it off of that. Since we know it's a symmetric graph, we want to make sure that we move the same distance to the right and the left of this middle point. So we're going to go to 1 and 2 on the right side, and -1 and -2. So as we build upon this idea of how to graph a parabola and that number adjusts, we will adjust our domain accordingly. So we'll not always be those 5 numbers. All right, to find our range, we're going to plug these values in one at a time for x. I'm going to start with the number that I know is my vertex, so we're going to go 3 times 0 squared, which should in this case give us a 0. So that's the smack dab center of our graph. However, as we move out, we should notice something with the symmetry. I'm hoping that when we plug these values in, that we notice they're the same. And then we also have a similar occurrence when we plug these in. So if we do those values, so let's do the 1 and the -1 first. When we square a negative, it becomes positive. So both of these just end up being 3 times 1, which is 3. So we do end up getting the same value for those. When you plug 2 and -2 in, you should get 12 and -12. Sorry, 12 on both, sorry. All right, so that's step 1. We're going to make a table of values. I know the end goal is to see what the 3 did to the graph in comparison to our parent function, but we first got to get a graph down so that we can kind of look at how that looks. So once we have our points, step 2 is just to plot those. If you get points that don't fit, don't worry about adjusting your graph. As long as you have the vertex and at least one other pair of points, you should be good to go. So our vertex is right here at our origin. Our next set of points moving out is at 1, 3 and -1, 3. So you'll notice they are symmetric over that axis of symmetry. And then our next points will be at 2, 12 and -2, 12, but I'm not going to graph those right now. All right, so once you have your points down, your goal is to draw a smooth curve to connect this. It's kind of hard to do on an iPad. It might be easier if you have paper. But it should kind of look like a U. It doesn't have to be perfect. And then like with all of our other graphs, it does have arrows at the end. So it's going on, up and to the left and up and to the right forever, which is why we need our arrows. So that's our graph. So if all I asked you to do was to graph, that's where you would stop. So this is the equation, or the graph of the equation y equals 3x squared. So now our last step here is to compare this to the parent function. So what I'm going to do is I'm actually going to copy and paste this on. And if you're not on Notability, don't worry about this. You can just kind of look in here and we can write down what our comparison is. But I'm going to paste this on so that we can compare it. So the green graph is the graph we just got done, and the purple is our parent function. So the question becomes, what happened to the graph when we went from y equals 1x squared and we changed it to a y equals 3x squared? I'm hoping what you're thinking in your head is that it made the graph narrower. So what we like to say is when this leading coefficient, the absolute value of it, is greater than 1, what it does to the graph is it makes it narrower. You're going to see when you get to your worksheet that I've listed out all the possible things that could happen when you make this comparison, and that's what you're looking for should narrower be the case. All right, so let's do this all again and see if we can find another way in which the graph can change. So now what we're going to do is we're going to adjust the leading coefficient so that it is less than 1. Again, for the graphs that we're doing today, our vertex is going to have an x-coordinate of 0. So like we stated before, we're just going to go 2 to the right, so at 1 and 2, and then 2 to the left, and plug these in accordingly. We should get 0 when we plug 0 in for x. We get a negative 0.25 when we plug 1 and negative 1 in. And we get a negative 1 when we plug 2 and negative 2 in. Again, you see that symmetric part to our points, which is important to check to make sure you have done those things accurately. So next, we're going to plot our points. So we're at 0, 0. 1, negative 1/4, negative 1 and a negative 1/4, and then 2, negative 1, and negative 2, negative 1. So there's our points. Now we connect the dots with a smooth curve. Oops, make that a little thinner. So hopefully your brain's kind of already wrapping itself around how this is different from our parent function. So I am going to place that back in here from the first page. Again, you don't need to write it in if you don't want to. So the purpose of drawing this is for comparison, so we get an idea of what happens. And there's actually two things that are happening here. So first, let's focus on what the negative did. Something we're going to talk a lot about is the orientation of the graph, whether it's opening up or down. You're going to notice when that number is positive, it opens up. When we make this leading coefficient negative, it's going to open down. So that's one way it can differ from our parent function. The other thing we want to point out is what the 0.25 did. So when we make this leading coefficient less than 1, the absolute value of it, you're going to notice that it makes the graph wider. So we have a way to make it narrow. We have a way to make it wide. It won't do both. It'll be one or the other if it does that. We have a way to flip it over our x-axis or have it open down. And then last but not least, we're going to look at how to translate our graph. All right, so now we're going to leave A alone. So you're going to notice in this last one, we aren't changing it. It's still a 1. But what we would like to do is add something on. So in this particular case, we're going to add a 5. So one last time, going through our steps. Hopefully this is going to, by the time you're done with these notes and with your homework, you're going to have a pretty good rhythm with graphing. So again, we're going to put our vertex right in the middle. And then we're going to adjust our domain accordingly. So since we're at 0, we're going to go 2 to the right and 2 to the left and plug these in one at a time. You should get 0, 5 as your vertex. I believe when you put 1 and -1 in, you should get 6. And you would put 2 and -2 and you should get 9. Now I've adjusted the x-axis, so we should be able to get these points pretty close to fitting on here. So step 2, go ahead and plot your points. So we're at 0, 5. 1, 6, and -1, 6. Again, you'll see that they kind of reflect across your y-axis since it's symmetric. And then 2, 9, which I believe is just one spot above. And those should be the dots for y equals x squared plus 5. So now we're going to connect that with a smooth curve. Let me try that again. Not forgetting our arrows. All right, then our goal is to compare this to the parent function. So I'm going to bring this down and place it on the origin there. So green is our new function, purple's our parent. So actually, it's kind of hard to see. Let me actually show you. The shape of this graph hasn't changed from the parent. So if I place the parent right over the top, they're the same shape. So we have not created something that gets wider or narrower because we didn't change the leading coefficient at all. It stayed as a 1. However, what we did change, which is the third and final way we're going to compare, is we added a C on that wasn't just a 0, which is why the other ones didn't have a number. So when we make this comparison, we're going to recognize that this plus 5, you could just say it moves, but the mathematical term is it translates, or it shifts, but translates a math term. It's going to translate up when it's positive. But the other option is that it would translate down, which is what you would do if it was a minus. So in this particular case, this one moved up 5 since it was a plus 5. All right, that's our first set of notes. Yay, math. Happy